at a target. A model with high bias is like aiming consistently in the wrong direction. A model with high variance is like throwing darts all over the place.
So we need a model that's accurate, meaning it hits the target A and D, consistent, meaning it hits the same spot repeatedly.
Precisely, and finding that balance is the challenge.
How do we actually measure bias and variance?
There are statistical techniques for that, but
Yeah.
the main thing is to find that sweet spot between the two.
Okay, so it's all about finding that Goldilocks zone. Not too biased, not too variable, but just right. The book then delves into this Vapnik-Chervonenkis theory, or VC theory. What is that all about?
VC theory gets pretty deep, but it's a way to analyze how complex a set of classifiers is and how that affects its ability to generalize to new data.
So it's like a measure of a model's learning capacity.
Exactly. And a key concept here is the VC dimension. It measures the complexity of the model.
Yeah.
A higher VC dimension means the model can learn more complex patterns, but also runs a higher risk of overfitting.
So it's a double-edged sword.
Exactly. And to help us navigate this, the book introduces this idea of structural risk minimization, or SRM. It's all about balancing the fit to the data with the complexity of the model to make sure we don't overfit.
Okay, SRM sounds like a useful principle. Now, on to Chapter 9, Dimensionality Reduction. Feels like we're cleaning house.
Exactly. High-dimensional data can be a nightmare. Too many features can make it hard to analyze, to visualize, and it can lead to overfitting. It's like trying to find a needle in a haystack. The more hay you have, the harder it gets.
So dimensionality reduction is about simplifying things without losing important information. What are some common strategies?
There are two main approaches. Feature selection, where we choose a subset of the most informative features, and feature extraction, where we create new features by combining the original ones.
So feature selection is like picking the all-star players for a team, and feature extraction is like blending a bunch of fruits into a smoothie. We get the essence of the original ingredients in a more compact form.
Perfect analogies.
So less is more.
Often, yes. Dimensionality reduction can make the analysis simpler, the visualization clearer, and it can help prevent overfitting.
Okay, that makes a lot of sense. The book then delves into principal component analysis, or PCA. That's a popular feature extraction technique, right?
Yep. PCA is like finding the directions in the data where there's the most variation, the most information, and then focusing on those directions. It's like rotating the data to find the most informative perspective.
So instead of looking at the data from every angle, we're finding the best viewpoints.
You got it.
And the book also mentions multidimensional scaling, or MDS. What's that one about?
MDS is another technique for simplifying the data while preserving the relationships between the data points. It's about keeping the distances between points as accurate as possible, even in a lower dimensional space.
Okay, so PCA is like finding the most expressive axes, and MDS is like preserving the relative distances.
Got it. Now, Chapter 10 introduces us to clustering.
Clustering. This is where we start to bring order to the chaos.
Sounds like my kind of chapter. Clustering is about grouping similar data points together. Think about organizing books on a shelf by genre or color.
Definitely need to do some clustering on my bookshelf. So what are some common clustering algorithms?
K-means is a classic. It's like you have a bunch of magnets on a table and metal objects are drawn to them. K-means finds those cluster centers and groups the data points around them.
So we're basically finding those centers of gravity that pull similar data points together.
Exactly. And choosing the right number of clusters is important. Too few and we oversimplify. Too many and we overfit.
Finding that balance again. What other clustering methods are out there?
The Gaussian mixture model, or GMM, models each cluster as a Gaussian distribution. Imagine you're drawing circles on a map to represent the density of different populations. That's kind of what GMM does.
So mapping out those clusters as probability distributions, okay, that's cool. And then there's hierarchical clustering, which builds a tree-like structure.
Yep. Think of it like a family tree, showing how individuals are related. Hierarchical clustering gives you this hierarchical view of the data so you can zoom in and out at different levels.
Okay, so lots of ways to group things based on their similarities.
Got it.
Chapter 11 marks a bit of a shift. We're moving from categorization to prediction with regression.
That's right. While classification is about predicting a category, regression is about predicting a continuous value. Like instead of saying, this house is in the luxury category, we're saying, this house is worth approximately X dollars.
So predicting a specific number on a scale.
Exactly. And just like with classification, there's this idea of an optimal regression function, the one that gives us the most accurate predictions.
So we're still striving for accuracy, just in a different way. What are some of the go-to techniques for regression?
Linear regression is a classic. It assumes a straight line relationship between the features and what we're trying to predict. Imagine drawing a straight line through a scatter plot of data points, trying to fit the line as close as possible to all those points.
Simple but effective. But what if the relationship isn't a straight line?
That's where things get more interesting. Basis function regression lets us use more complex nonlinear functions. Think of bending that straight line into a curve to better fit the data.
So more flexibility.
Mm.
And then there's Gaussian process regression. That one sounds intimidating.
It can seem that way, but the basic idea is that we're modeling the thing we're trying to predict as a Gaussian process, which lets us make predictions with a sense of how certain we are about them. Imagine drawing a curve through those data points, but also having a band of uncertainty around that curve, showing the range of possible values.
So acknowledging that our predictions aren't perfect, especially with complex data.
Exactly. And just like with classification, overfitting can be an issue here. We need to choose our model carefully.
Okay, starting to see some common themes here now.
Yeah.
Chapter 12 takes us to the cutting edge. Physics-informed machine learning. This sounds like we're merging the digital and physical world.
It really is. It's about combining the power of data-driven models with our knowledge of physics.
Can you give me a concrete example?
Sure. Imagine you're trying to predict the trajectory of a ball. Traditional machine learning might just look at past trajectories and try to learn from those. But with physics-informed learning, we can also incorporate the laws of motion gravity, air resistance, all that, to make more accurate predictions.
This is like giving the model a physics lesson.
Exactly. And that can lead to much better results, especially when we don't have a ton of data.
Okay, I'm starting to get the idea. The book introduces these things called physics-informed neural networks, or PNNs. What are those?
PNNs are neural networks that are trained to not only fit the data, but also to obey the laws of physics. Imagine you're training a network to predict the temperature in a room. You could also make sure that it takes into account the laws of heat transfer, how heat flows from one place to another.
So, it's like having a physics professor supervise the training process. What kinds of problems can we solve with these PNNs?
Oh, all sorts. Predicting fluid flow, optimizing designs, all kinds of things in science and engineering.
Wow, this is opening up a whole new world of possibilities. The book also mentions using Gaussian processes, or GPs in this context. How do those fit in?
GPs are great because they give us a way to quantify uncertainty, how confident we are in our predictions, so they complement PANs nicely.
Okay, so PNNs bring the physics knowledge, and GPs help us deal with uncertainty. Got it. Now let's talk about the specific examples the book uses to illustrate all this. Bioinformatics and materials informatics.
These are great examples of how this stuff is being used to solve real problems in cutting-edge fields.
All right, let's start with bioinformatics. How is machine learning changing our understanding of biology and medicine?
Bioinformatics is all about using computers to analyze biological data, and there's a ton of data in biology. But making sense of it all, that's the challenge.
It's like having a giant library, but no way to find the books you need.
Exactly. Machine learning gives us those tools. It helps us find patterns, make predictions, and ultimately understand these complex biological systems better.
The book mentions an example of classifying diseases based on gene activity. Can you explain that a bit more?
Our genes are like the instruction manual for our bodies, and how active they are, whether they're turned on or off, plays a huge role in health and disease.
So, by looking at patterns of gene activity, we can potentially identify what's going wrong and maybe even predict someone's risk of developing certain diseases.
That's the idea. Machine learning can sift through tons of genomic data, finding those subtle patterns that humans might miss. It's revolutionizing diagnostics, helping us catch diseases earlier and develop more targeted treatments.
That's incredible. It's like using machine learning to decode the language of our genes. What other applications are there in bioinformatics?
Oh, so many. Designing new drugs, predicting protein structures, understanding the microbiome, even personalizing medicine based on someone's unique genetic makeup.
It's amazing how much potential there is. Now let's shift gears to materials informatics. How is machine learning impacting the world of materials?
Materials informatics is a newer field, but it's already making waves. Traditionally, developing new materials has been slow and expensive, lots of trial and error.
So machine learning is speeding things up.
Exactly. We can use it to analyze massive data sets of material properties, figure out how those properties relate to the material's structure and composition, and then use that knowledge to design new materials with specific properties we want.
The book gives an example of predicting the properties of materials based on their composition. Can you walk me through that?
Sure. Imagine you're trying to create a new alloy that's super strong and lightweight, for example. Machine learning can look at data from existing alloys, see how the composition and processing techniques affect the final properties, and then predict what would happen if you tweak things a certain way.
So instead of just mixing things randomly and hoping for the best, we can use data to guide our experiments.
Exactly. It's much more efficient and can lead to some really amazing discoveries.
This is really cool. What other applications are there in materials informatics?
Oh, tons. Optimizing manufacturing processes, predicting how long a material will last, even designing self-healing materials.
Self-healing materials. That sounds straight out of a sci-fi movie.
Yeah.
What are some of the challenges in this field?
One of the biggest is just getting good data. Materials data can be scattered, inconsistent, and hard to access.
So data quality is key, as always.
Absolutely. And of course, we always need to remember that these models are just tools. We need to validate their predictions with real-world experiments and use our judgment and expertise to interpret the results.
Okay, that's a good reminder. Now, Chapter 13 seems to bring everything together, revisiting some of those big picture ideas.
That's right. It's all about the interplay between data, models, and human judgment. Machine learning can give us incredibly powerful insights, but ultimately it's up to us to decide how to use those insights.
It's not about replacing human decision-making, it's about augmenting it.
Exactly. The book talks about human-in-the-loop systems where the machine learning models give us recommendations, but humans are still in control.
That makes sense. It's about finding the right balance. What else does the chapter highlight?
Explainable AI is a big one. It's about making these models more transparent so we can understand why they make the decisions they do.
So it's not just about getting an answer, it's about understanding the reasoning behind it.
Well,
That's crucial for building trust, right?
absolutely. And then the book touches on the future of machine learning, the trends, the challenges, the possibilities.
Okay, what are some of the big things on the horizon?
Well, deep learning is still evolving rapidly. Reinforcement learning, where the algorithm learns by interacting with its environment, is another exciting area. And then there's quantum computing, which could completely change the game in terms of what's possible.
Wow, it sounds like the future of machine learning is going to be wild.
It definitely is. And that brings us back to an important concept, the no free lunch theorem.
Remind me what that one is again.
It basically says there's no one algorithm that's best for every problem. It's all about choosing the right tool for the job.
So no magic bullet.
Nope. We need to understand the strengths and weaknesses of different approaches and make informed choices. And that's going to be even more important as the field continues to evolve. It's amazing to think about how much machine learning is already part of our daily lives.
I know, right? Like personalized recommendations, spam filters. We don't even think about it anymore, but there's some serious machine learning going on behind the scenes.
And it's only going to get more pervasive.
Exactly. Speaking of which, what about those really big, mind-blowing possibilities, the ones that still feel like science fiction? The book hints at how machine learning could revolutionize things like robotics and artificial intelligence.
Oh, absolutely. Robotics is a great example. Think about how robots have been used traditionally very repetitive tasks in controlled environments. Machine learning changes everything.
Yeah, like giving them the ability to learn and adapt.
Exactly. Now we can create robots that can handle new situations, learn from their experiences, even interact with the world in a more human-like way.
It's like taking them out of the factory and dropping them into the real world, where they have to think on their feet. I think the book even mentions self-driving cars as an example.
Self-driving cars are a perfect illustration of how machine learning is pushing the boundaries. They have to process so much information from their sensors, make decisions in real time, navigate complex environments.
It's mind-boggling. All that data processing, and they have to react instantly to anything that happens on the road. It's like a supercomputer on wheels.
That's a great way to put it. And as the technology gets better, self-driving cars have the potential to completely change transportation.
Safer, more efficient, and maybe even more accessible for people who can't drive themselves. Okay, now let's talk about the big one. Artificial intelligence. How is machine learning shaping the future of AI?
Well, the whole idea of AI is to create machines that can do things that normally require human intelligence, right? Things like understanding language, recognizing images, making decisions. Machine learning is at the heart of a lot of the recent progress we've seen in AI.
So we're basically teaching machines to think like humans.
In a way, yes. Machine learning algorithms can analyze massive amounts of data, find patterns, and learn to make predictions or decisions based on that data. It's led to incredible breakthroughs in areas like natural language processing, image recognition, even AI that can beat humans at complex games.
I remember reading about those language models that can generate text that sounds like a human wrote it. It's
I
crazy.
know, right? Models like GPT-3 can produce text that's not just grammatically correct, but also creative and engaging. Sometimes it's hard to tell if a human or a machine wrote it.
It's both fascinating and a little creepy. What are some of the things we could do with these language models?
The possibilities are pretty mind-blowing. Imagine AI assistants that can write emails, articles, even books, all tailored to your specific needs, or chatbots that can have natural, meaningful conversations, providing customer service, companionship, even education.
It's like they could change how we communicate and learn and even create.
Exactly. And as with any powerful technology, we need to be careful, make sure we're using it responsibly and ethically.
Absolutely. Well, this whole deep dive has been an amazing journey. We started with the basics of pattern recognition and machine learning, explored some really cutting-edge techniques, and even got a glimpse into the future of the field.
It's been a great exploration. This book really lays a strong foundation and shows us just how much potential there is.
Before we sign off, I want to come back to something that really stood out to me from the book, the importance of the human element in all this. It's not just about the algorithms and the data. It's about using these tools thoughtfully and ethically to make the world a better place.
I couldn't agree more. As powerful as these technologies are, we need to make sure they're used for good and that we're aware of the potential downsides.
It's about finding that balance, harnessing the power of these tools while staying grounded in our values and our humanity. I think it's a great note to end on. So, to everyone listening, thank you for joining us on this deep dive. We hope it sparked your curiosity and given you a new appreciation for the incredible world of pattern recognition and machine learning.